Hurricane Melissa made history as the second strongest Atlantic storm ever recorded. But what happened to the ocean floor beneath its 185 miles per hour? Winds is rewriting everything seismologists thought they knew about storm-earthquake connections. When the Category 5 monster's eye wall passed over the Caribbean Sea, it generated pressures equivalent to dropping a mountain on the seafloor every few seconds. The result? Scientists have detected fracture patterns extending over 200 miles from Melissa's path, cracks in the ocean floor that are now generating seismic pulses unlike anything in geological records. Dr. Elena Vasquez, who led the emergency research response, put it this way: "We're witnessing the birth of what we're calling megastormquakes, seismic events that could fundamentally alter our understanding of how Earth's surface and atmosphere interact." But here's the part that has the global seismic community in emergency sessions. These pulses aren't random. They're following patterns that suggest Melissa may have awakened something that's been building pressure beneath the Caribbean for centuries. What happens when those fractures connect with the Puerto Rico Trench, one of the most dangerous fault systems on the planet? Hurricane Melissa exploded onto the world stage on October 21st, 2025, forming over Caribbean waters that were abnormally superheated, a full 2 degrees Celsius above their historical averages. What happened next defied meteorological expectations. Within just 48 hours, Melissa transformed from a tropical depression into a Category 5 behemoth. Its central pressure plummeted to an astonishing 892 millibars, the third lowest pressure ever recorded in an Atlantic hurricane, and tying with the historic 1935 Labor Day hurricane. Only Hurricane Wilma's 882 millibars in 2005 was lower, but pressure tells only part of the story. Melissa's sustained winds reached 185 miles per hour, winds so powerful they literally pushed the ocean aside, creating pressure differentials that would prove catastrophic below the surface. For comparison, these winds could strip a forest bare in minutes, shred concrete structures, and send vehicles airborne like toys. The storm's path carved a corridor of destruction that will haunt the Caribbean for generations. Jamaica took the first direct hit on October 28th, enduring what officials called the island's darkest day since records began 174 years ago. The eye made landfall near Kingston with the full fury of those 185 mile per hour winds intact. Nothing in Jamaica's meteorological history had prepared the island for this level of devastation. Less than 24 hours later, eastern Cuba faced Melissa's wrath. Cuban authorities had evacuated more than 600,000 people, including from Santiago, the country's second largest city. Even with those precautions, the damage was catastrophic. Buildings that had withstood previous Category 5 storms like Hurricane Dorian crumbled under Melissa's unprecedented power. By October 30th, Melissa had turned northeastward, sparing the US mainland from a direct hit, but bringing torrential rains to the mid-Atlantic and New England. The Bahamas, however, could not escape. Grand Bahama Island, still recovering from Hurricane Dorian's devastation in 2019, faced storm surges exceeding 20 feet. What makes Melissa historically significant is not just its raw power, but its place in a disturbing trend. This was the third Category 5 hurricane of the 2025 Atlantic season, making it only the second time in recorded history that more than 2 Category 5 storms have formed in a single season. The only other year to achieve this dubious distinction was 2005, with its quartet of monsters, Emily, Katrina, Rita, and Wilma. The 2-year period of 2024 to 2025 marked only the second time that the Atlantic has experienced consecutive years with multiple Category 5 hurricanes. The previous 2-year period was 1932 to 1933, nearly a century ago. This pattern of increasingly frequent Category 5 storms aligns with climate scientists' predictions about warming ocean temperatures creating ideal conditions for explosive storm development. Perhaps most tellingly, 4 out of 5 hurricanes in the 2025 Atlantic season reached Category 4 or 5 status, the highest percentage ever observed. Each data point confirms what climate scientists have been warning. Our warming oceans have fundamentally changed the rules of hurricane formation. But as unprecedented as Melissa was from a meteorological standpoint, what happened beneath the ocean's surface would prove even more extraordinary. As Melissa's eye wall churned across the Caribbean Sea, a team of seismologists led by Dr. Elena Vasquez at the Caribbean Geological Institute was monitoring a network of ocean floor sensors. These sensors, part of a long-term project studying tectonic movements in the region, were not designed to detect storm impacts. Yet what they recorded in real time left the scientific team speechless. Our instruments began detecting seismic signals unlike anything we had ever seen, Dr. Vasquez reported. Initially, we thought there was a malfunction in the system, but as data poured in from multiple sensors, we realized we were witnessing something unprecedented. The seismic signals were not random noise. They were organized rhythmic pulses occurring at 47-minute intervals, a pattern so precise it seemed almost mechanical. What's more, these were not the familiar signatures of tectonic movement. These were something new, something that bridged atmospheric science and geology in ways never before documented. To understand what happened, we need to grasp the extraordinary physics at work. Melissa's 185 mph winds and record low 892 millibar pressure created a rarely seen phenomenon: extreme wave loading differential. As the hurricane passed, it did not just create surface waves, it generated profound pressure differences on the ocean floor below. At its peak intensity, explains Dr. Vasquez, Melissa was effectively lifting and dropping the equivalent weight of a mountain. On the seafloor, every few seconds, imagine a pressure hammer pounding relentlessly on the same spot, except this hammer weighed billions of tons and was striking across hundreds of square miles simultaneously. Previous research into what scientists call storm quakes had documented how hurricanes can generate seismic activity equivalent to a magnitude 3.5 earthquake. But these are typically isolated, transient events that dissipate quickly once the storm passes. What Melissa triggered was dramatically different. Satellite gravitometry data, which measures minute changes in Earth's gravitational field, revealed something shocking. The ocean floor had physically fractured along a 200-mile corridor that traced Melissa's path. These weren't superficial cracks, but deep fissures extending several hundred feet into the Caribbean plate. The most disturbing discovery came from bathymetric scanning performed in Melissa's wake. The seafloor topography had fundamentally changed. Areas that were once flat showed new ridges and depressions. Sections that had been stable for centuries had shifted vertically by as much as 6 feet. One undersea plateau had completely split, creating a new channel where none had existed before. But the fracture pattern wasn't just following Melissa's track, it was spreading outward like cracks in glass, reaching toward existing fault systems. Most concerning was a series of fractures extending northeastward toward the Puerto Rico Trench, the deepest part of the Atlantic Ocean and home to one of the most dangerous submarine fault systems on the planet. What we're seeing is essentially an atmospheric geological coupling event, explains Dr. Vasquez. The storm's energy transferred directly into the Earth's crust, creating what we're now calling mega stormquakes. Unlike normal stormquakes, which typically measure around magnitude 3.5 and dissipate quickly, these are sustained seismic events that continue generating pulses days after the storm has passed. The most alarming aspect? The pulses aren't weakening. They're strengthening and synchronizing across multiple fissures. It's as if Melissa has awakened something that had been dormant beneath the Caribbean Sea for centuries. To understand the full implications of what Hurricane Melissa has triggered, we need to examine the complex tectonic landscape of the Caribbean region. The Caribbean sits at the junction of 4 major tectonic plates: the North American, South American, Caribbean, and Cocos plates. This complex boundary system has created a network of fault lines that crisscross the region both above and below the sea. The Puerto Rico Trench, lying just north of Puerto Rico and the Virgin Islands, represents one of the most significant seismic dangers in the Western Hemisphere. At 8,376 meters deep, over 27,000 feet, it's the deepest point in the Atlantic Ocean. So profound that if Mount Everest were placed inside, its peak would still be over 1,000 feet underwater. But it's not just the trench's depth that concerns scientists, it's its geological makeup. The trench marks where the North American plate is being subducted beneath the Caribbean plate, creating enormous potential energy. Historically, this system has produced catastrophic earthquakes, including a suspected magnitude 8.1 event in 1787 that devastated the region. The Puerto Rico Trench has been unnervingly quiet for decades, explains seismologist Dr. Rafael Mendez at the Puerto Rico Seismic Network. This doesn't mean it's safe. It means pressure has been building. Many of us have been concerned that when it finally releases, the consequences could be devastating. The trench isn't an isolated feature. It connects to a vast network of submarine fault systems, including the Septentrional Fault, the Bunce Fault, and the Muertos Trough. Together, these form a complex, three-dimensional web beneath the Caribbean Sea. When one section moves, it can transfer stress to others, potentially triggering a cascading failure. Historical precedent makes this scenario particularly concerning. In 1692, a major earthquake collapsed much of Port Royal, Jamaica, causing parts of the city to slide into the sea. What's often overlooked is that this event wasn't isolated. What we're seeing now with these synchronized pulses shows disturbing similarities to historical accounts preceding major Caribbean earthquakes, Dr. Mendez notes. The 47-minute rhythmic pattern is especially troubling because it suggests a resonance effect building across the fault network. The satellite gravitometry data reveals something else alarming: density changes in the seafloor structure around the fracture zones. These indicate fluid migration within the Earth's crust. Essentially, water is penetrating deeper into the fault systems. This is significant because water acts as a lubricant between fault planes, potentially allowing them to slip more easily. The fractures created by Melissa are now acting as conduits, allowing seawater to reach areas of the fault system that were previously dry and locked. As this water penetrates deeper, it could effectively unlock sections of the Puerto Rico Trench that have been building pressure for centuries. What we're witnessing may be the beginning stages of fault reactivation, warns Dr. Vasquez. The synchronized pulses appear to be propagating toward the Puerto Rico Trench at a rate of approximately 4 miles per day. At this pace, they could reach the main fault system within weeks. Already, smaller satellite faults connected to the main Puerto Rico Trench are showing increased activity. Monitoring stations have detected micro-earthquakes occurring with increasing frequency along the north coast of Puerto Rico, a phenomenon typically seen before larger seismic events. The most concerning development is that the fracture network has begun to intersect with deeper magma chambers beneath the eastern Caribbean, while Puerto Rico itself doesn't have active volcanoes. The eastern Caribbean islands like Dominica and Montserrat do. Pressure changes in these volcanic systems could potentially trigger increased activity. We're essentially watching a slow-motion disaster unfold beneath the Caribbean Sea, Dr. Vasquez states grimly. The question isn't if these systems will release their built-up energy, but when and how catastrophically. As scientists race to understand and model the unfolding seismic crisis beneath the Caribbean, a terrifying timeline is emerging, one that connects Melissa's fracture network to potential catastrophic events in the coming months. The mechanism driving this crisis is known as pressure fracture cascade, a process where initial cracks propagate, connect, and eventually trigger much larger fault systems to fail. It's analogous to how a small crack in a windshield can spread across the entire surface. Computer simulations using data from the fracture network show an alarming projection. As the fissures continue extending toward the Puerto Rico Trench, they're creating what seismologists call stress shadows, areas where pressure is being redistributed across the fault system. What's particularly concerning, explains Dr. Vasquez, is how these fractures are connecting. We're not seeing random patterns, they're following existing weaknesses in the Caribbean plate, creating linkages between previously isolated fault segments. This connectivity is crucial because it effectively transforms smaller, manageable fault segments into a single, much larger system capable of generating significantly more powerful earthquakes. Historical records suggest that when fault segments connect in the Caribbean, the results can be catastrophic. The population centres at greatest risk lie directly in the path of this unfolding crisis. Puerto Rico, with its 3.2 million residents, sits immediately south of the Puerto Rico Trench. The Dominican Republic, with over 10 million people, faces dual threats from both the northern fault systems and the Muertos Trough to its south. Jamaica, still reeling from Melissa's direct impact, now faces a new danger from seismic activity. Based on current propagation rates, we project that the fracture network could reach critical connection points with the Puerto Rico Trench within 45 to 60 days, Dr. Mendez warns. If that happens, we could see a major rupture event, potentially magnitude 7.5 or greater. But the earthquake itself might not be the greatest danger. The real catastrophic potential lies in tsunami generation. The Puerto Rico Trench's unique geometry makes it particularly efficient at producing tsunamis when disrupted. Historical precedent again provides a sobering reference point. In 1867, an earthquake estimated at magnitude 7.5 struck near the Virgin Islands, generating a tsunami with waves reaching 7 meters high. That event originated from a much smaller fault segment than what's currently being activated. Modern tsunami models incorporating Melissa's fracture network project something far more dangerous. If the Puerto Rico Trench experiences a full segment rupture, waves could reach 15 to 20 meters, 50 to 65 feet, along northern Puerto Rico, higher than a 5-story building. Even more concerning, such a tsunami would reach shores in as little as 10 to 15 minutes after the earthquake, leaving minimal evacuation time. The public needs to understand that we're not talking about a distant possibility, stresses tsunami expert Dr. Maria Gonzalez at the Caribbean Tsunami Warning Center. We're watching the preliminary stages of a process that has historically led to major seismic events in this region. What makes this situation particularly unprecedented is the direct connection between atmospheric pressure from Hurricane Melissa and geological pressure in the fault systems. This coupling effect could potentially accelerate normal fault cycles that typically take centuries to develop. Adding to the complexity is the recently discovered phenomenon of earthquake-induced pressure waves affecting neighbouring volcanic systems. If a major rupture occurs along the Puerto Rico Trench, it could potentially trigger increased volcanic activity across the Eastern Caribbean's active volcanic arc. Time is now the critical factor. Monitoring stations across the Caribbean have been placed on highest alert, with continuous data feeds being analysed around the clock. International scientific teams are deploying additional seafloor sensors to track the fracture propagation with greater precision. Emergency management agencies throughout the Caribbean are updating evacuation plans, with particular focus on coastal communities that would have minimal warning time in a tsunami scenario. But the sheer scale of the potential disaster poses unprecedented challenges for regional governments already strained by Melissa's direct impacts. We're in uncharted territory, Dr. Vasquez acknowledges. The geological record shows similar coupling events may have occurred in the distant past, but never in modern times with our current population density and infrastructure vulnerability. As fractures continue spreading and seismic pulses intensify, the Caribbean region finds itself in a race against geological time, with millions of lives potentially hanging in the balance. The unprecedented interaction between Hurricane Melissa's atmospheric power and the Caribbean's complex fault systems has opened a new chapter in our understanding of how Earth systems interconnect. What began as a meteorological event has triggered geological consequences that could reshape our understanding of natural disaster cascades. Monitoring efforts have now expanded to include international scientific teams deploying specialized equipment across the region. Advanced seismic arrays, ocean bottom seismometers, and satellite monitoring systems are providing real-time data on the evolving situation. Yet significant questions remain unanswered. How will the fracture network continue to evolve? Can the pressure cascade be mitigated before reaching critical fault junctions? What might trigger or prevent a major rupture event? As Dr. Vasquez notes, we're witnessing Earth systems coupling in ways we've theorized but never directly observed. The data we're gathering now will inform disaster science for generations. What happens when atmospheric pressure meets geological pressure points? Subscribe to Earth Attacks for exclusive updates as scientists race to understand this developing crisis and predict its potentially catastrophic consequences for the Caribbean region and beyond.